This is part 3 of a series on CNN. In this video, we will look at 2D convolution. 2D convolution can be used for RGB image data. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In this video, we will take a closer look at a CNN model using 2D convolutional layers. Let's take a look at how the two-dimensional convolutional layer works. Let's take a look at the structure of the input and output of a 2D convolutional layer. And we will also look at a two-dimensional pooling layer. And let's use these layers to classify the CFAR10 images. Again, 2D convolution is typically used for an RGB image dataset, and the filters slide in 2 dimensions. The structure of the input data X is as follows. This is a single RGB image. The input data X contains multiple RGB images. The input data used in 2D convolution has 4-dimensional structure. In CNNs, it's very important to understand the shape of the input and output arrays. The first dimension is the batch size of the input data. The second dimension is the number of rows of an RGB image, N. The third dimension is the number of columns of an RGB image, M. The last dimension is the number of color channels, C. C in an RGB image is 3, red, green, and blue. C doesn't have to be 3. It can be greater than 3 or less than 3. Channel C can be placed in the second dimension of the array, but is typically placed in the last dimension, as shown in this figure. In this example, N is 6, M is 5, and C is 3. Padding can be added to the input data on the top, bottom, left, and right. In this example, no padding is applied. We covered padding in the first video of this series, so we won't go into that here. The filters used in 2D convolution have a 4-dimensional structure. Each filter has a 3-dimensional structure like this. The last dimension of the filter should match the last dimension C of the input image. A 3D filter is applied to a 3D image. Each filter consists of RGB filters of size K1 by K2, a red filter, a green filter, and a blue filter. Each RGB filter is applied to each RGB channel of the image. There are such filters. Compute the cross-correlation or convolution between the input data and these filters. Each filter scans the input data from top to bottom and left to right, computing cross-correlation or convolution. This gives us the 3D feature map like this. Cross-correlation and convolution were also covered in the first video of this series. We then sum these matrices along the channel axis. Then we can obtain a 2D feature map like this. A bias can be added to this results. Each of the R filters produces a feature map as follows. Combining these feature maps into one produces the final feature map, which is the output of the 2D convolutional layer. The final feature map for a single RGB image has a 3-dimensional structure like this. Therefore, the feature maps of multiple RGB images have a 4-dimensional structure. The last dimension R is the number of filters. In the next layer, R corresponds to the channel C. As mentioned earlier, the last dimension can be greater than 3. This feature map can be fed into the next 2D convolutional layer, or 2D pooling layer. This is the number of trainable parameters in a convolutional layer. Next, let's look at the 2D pooling layer. A pooling layer downsamples the output feature maps of the convolutional layer to produce new feature maps of smaller size. The feature map, which is the output of the 2D convolutional layer we looked at on the previous page, looks like this. In this example, the feature map consists of 3 4x3 matrices. Let's use a 2D max pooling filter of size 3x2. This filter is applied to each matrix in the feature map. First, apply this filter to the first matrix of the feature map. And select the maximum value in the area covered by this filter. This will be the first element value of the downsampled feature map. Then move this filter to the right by 1 pixel. In this example, the stride value is set to 1. The maximum value in this area is 2.6. This will be the next element value in the downsampled feature map. Next, move this filter down by 1 pixel. The maximum value in this area is 2.5. Then move this filter to the right by 1 pixel. The maximum value in this area is 3.0. Do the same for the remaining 2 matrices. And then we can get the downsampled 3D feature map as follows. Adding the batch dimension makes this feature map a 4-dimensional structure. This is the 2D max pooling process. This feature map can be fed into another 2D convolutional layer or into a feed-forward network, as in this example. This feature map is reshaped into a 2-dimensional structure and then fed into a feed-forward network. The feed-forward network performs classification or regression. You can also use 2D global max pooling, as in the example below. In this case, the size of the pooling filter is the same as the size of the feature map. This filter produces a 2-dimensional feature map like this. This feature map can be fed directly into a feed-forward network. This is an example of a simple CNN model using a 2D convolutional layer and a 2D pooling layer. Instead of a 2D max pooling layer, you can also use a 2D average pooling layer. Next, let's classify CIFAR10 images using 2D convolution. The CIFAR10 dataset consists of 60,000 color images with a 32 by 32 pixels resolution in 10 classes, with 6,000 images per class. There are 5 2000 training images and 1 in 1,000 test images. CIFAR10 classification is a more challenging problem than MNIST classification. Load the CIFAR10 dataset. The 10 categories are as follows. These are sample images. Each sample is a 32 by 32 by 3 RGB image. The first sample image is a horse, and the second sample is an automobile. Now let's build a 2D CNN model. I wrote a function that sequentially performs a 2D convolutional layer, batch normalization, ReLU activation, and a 2D average pooling layer. Create an input layer. The input layer receives four-dimensional data like this. The last dimension is 3, which is the number of RGB channels. And I performed image augmentation on the input data. This is to prevent overfitting. Add a random flip layer. This randomly flips the input images during training. The argument horizontal is a left-right flip, and vertical is a top-bottom flip. Only horizontal is applied here. I also added a random rotation layer. This randomly rotates the input images during training. Next, add a sequence of layers defined in above function 3 times. We flatten the output of the last pooling layer and feed that output into the feed-forward network. Create and compile this model. Let's take a look at the structure of this model. We'll take a closer look at the structure of this model on the next page. Fit this model to the training data. The structure of this model is as follows. The input layer receives multiple CFAR10 images. This is followed by the layers for image augmentation. Next, we have the layers defined in this function. The first convolutional layer has 16 filters of size 3 by 3 by 3. The last number 3 is the number of channels, which is the last dimension of the input data. The stride value is 1, and there is no padding. Let's use this formula to calculate the output size of this convolutional layer. N is 32, P is 0, K is 3, and S is 1. Then the output size will be 30. And the last dimension of this output is the number of filters. The number of trainable parameters can be calculated as follows. The 16 added at the end is the number of biases. Next, let's look at the output size of the pooling layer. The pool size is 2 by 2. If no stride value is specified, it will default to the pool size, i.e. 2 by 2. And there is no padding. Then the output size of the pooling layer will be 15. Pooling layers have no trainable parameters. The output of this pooling layer becomes the input to the next convolutional layer. This time, the number of channels is 16. Then the output size of this convolutional layer will be 13. 32 is the number of filters. The number of trainable parameters can be calculated as follows. In this way, we have a total of 3 convolutional and pooling layer sequences. Finally, we have the feed-forward network. The final output of this model is a vector of size 10, excluding the batch dimension. This is the number of categories in the CFAR10 dataset. Next, let's check the loss history and measure the accuracy of the test data. Finally, let's check out some misclassified images. The changes in losses are as follows. Both training loss and test loss are significantly reduced. And the accuracy of the test data is 0.7649. Without image augmentation, the loss changes are as follows. You can see that overfitting is occurring. Let's check the misclassified images. The first image is actually a deer, but was misclassified as a dog. Let's run this code. We got the following results. So far, we have looked at how 2D convolutional layer works and applied it to an RGB image classification problem. In the next video, we will look at 3D convolution.